Okay, so this Wednesday there's no scheduled test. However, the TA will be there. I'll just let you know. So there'll be WSC 105. So we got other lab activities in the other two rooms. So please go to WSC 105 if you got any questions related to your lab number 4, 105. Okay, you can simply go there if you need any help on lab number 4. And don't forget the tracing exercise, okay? And then after next week, the week after, we actually got your written test number 2. That's gonna cover inheritance. So whatever that we covered today and also on Thursday, they will be covered in written test 2 as well. Okay, I'll confirm the exact slides a little bit later, maybe after your fellow student in section B. So it's gonna be in sync between 2 sections. I'll confirm pretty soon, but you can definitely start studying for the materials that we have covered so far. And then the final week, we also got your programming test number 3. So that one will be the last test for the semester before the exam. And that one, they primarily will be based on lab number 4. So your best interest will be to really develop your lab number 4 steadily, right? Just to make sure you can complete your own solution before the submission deadline. And then I'll give you the solution walkthrough as usual. So you can also study that just to get prepared for the last test. And then our exam, it's actually pretty late, about December 16 or 17, I forgot exactly. But we can definitely maybe host some review session, to gather together and answer your questions. And also, I'll give you some example questions to try as well during the exam period. But anyway, so I'll reach out to you. It's still a little bit too early to talk about it. But just watch out for the semester calendar just to see what's going on in the course, right? Everything will be on schedule. Any questions? Yes? Sorry? You have written test number 2, which will be next Wednesday. That'll be the last one.
Okay, I thought there was another programming test.
That's right. Well, you can think about right now it's week number 10. So in week number 11 and 12, we got 2 tests. Yeah, on this calendar. Yeah, everything's on calendar. No surprise. All right, guys. Let's now get started. Okay. So today we're gonna dive deep into substitution, basically variable assignment. Especially we're going to consider inheritance hierarchy, right? So it's going to be a little bit intense. I'll try to visualize as much as I can, but if there's any point you really kind of get confused or get lost, it's better to stop me, right? So the stuff we talk about will be also very important that we're going to build up on Thursday as well. Okay, you can let me know. Otherwise, I'll just move on. All right, so last time we actually talked about the different scenarios where you can use a super keyword. So the bottom line, you simply cannot say super. You just cannot. You can only refer to the version that's overridden right above you. That's a parent class. Okay, just remember that. And then we talk about how you can visualize parents versus child object. That's something we'll see as well. It's a very important insight for you to keep in mind. When you visualize the parent object, let's say for the students, you got all the common attributes right here. And then when you visualize each child objects, like a resident student or non-resident student, part number 1, they inherit all the attributes from the student class, for sure. That's a common part. But in addition, they also got their own unique attributes, like a premium rate versus discount rate. So when you visualize the child objects, just pay attention to exactly the range of attributes that you will inherit. We also call that as the expectation. That's something we'll see as well today a lot. And then we talk about just how you can put the objects into play. So you got different dynamic type. So when you call Jim and Jeremy at the point of get tuition, you can see Jim dynamic type is resident students. Jeremy dynamic type is non-resident students. So that's why you're going to call different version of the get tuition. Right? That's something we have covered quite a few times. Hopefully getting more comfortable with it. And the modifiers is just about how visible you want your attributes, methods, or class to be. I would say this one here is a little bit diversion from the inheritance topic. So from now on, we simply assume all the classes might just be public. And also, all the classes we talk about related to inheritance, they will be put inside the same package. So we don't declare any modifier. However, this part of the lecture, you want to pay attention to the different options for attributes and for classes. That's something we talked about last time, right? Remember, there's also starter projects on the lecture site for you to play with as well, right? That's something you definitely want to study alongside. And of course, feel free to experiment in your lab number 4 and later on lab number 5 as well. That's exactly the place to play with these concepts you learned from the lecture. So that's about the either public or not public classes. Versus we got either private, package level, protected, related to inheritance, and also public, right, attributes. Also, we got a summary table right here. Right, if you got any trouble understanding, of course, the first thing you can try, rather than coming to me, I'll be happy to help you, but maybe the first thing you should try is try anything you have in doubt in Eclipse. Let Eclipse tell you whether things will compile. If you're not exactly sure what the message is about from Eclipse, you can come to me, and I can work it out together with you. All right. And then we talk about expectation. So whenever we talk about expectation here, it's really about when you declare a reference variable of certain type, that particular type has certain expectation. So expectation will simply be the list of attributes and methods you can call on that particular reference variable. So normally we'll just talk about, of course, private attribute wouldn't be included, right? In this case, we'll talk about there's no modifier, so in the same package. And to summarize this exercise over here, you can see that for student, you can see all the static type right here. Student, resident, student, non-resident student. All of them share the common expectation, this part here. Because that common expectation, like a name, registered courses, and etc., they're all inherited from the student class. That's why all of them have this part. And then in addition to it, for child class number 1, resident students, you also have premium rate and set premium rates, but not the other two. And for non-resident students, which is another child class over here, that one has discount rate and not set discount rate, but not the other two. Right? So we talk about expectation. You always want to think about what exactly is the expectation for a particular class. And we'll do one exercise just to start us with, just to emphasize this idea, using a different example, slightly more complicated. Hopefully you'll see that even more. So what you want to do is to really understand about this table here, redo it if necessary. And then polymorphism, dynamic binding, right? The conclusion is whenever you actually have some variable assignments, the left-hand side somehow will have to be the parents. And the right-hand side will somehow has to be child, right? That's kind of the conclusion we made. But we're going to make it even more systematic today. We're going to generalize the idea about parents into ancestor and child into descendants. That will be the ultimate rule that we're going to learn just today. All right, but the intuition that we spoke about last time is also very crucial. So make sure you also understand, right? You don't really want to just memorize like a brute force approach. That's not the way to go. And we talk about dynamic binding. So whenever you have a method call, let's say for this student object over here, at this point, right, you can see these two lines right here. These two lines are exactly identical, same method and also same context objects. But these two are going to exhibit different behavior at the runtime, simply because at the point of calling this get tuition here, dynamic type for S right here is resident students. At the point you call this line here, dynamic type for S is non-resident student right here. We did a tracing last time, so maybe for that part I wouldn't repeat. You can maybe catch up with the recording if you got any doubts, or just drop by. I still got my office hour tomorrow, 6 p.m. Okay. And pay attention to this table as well, just about how you can trace about the dynamic type for a particular variable. Static type never changes. Okay. Okay, and then reminder, compilation, you only look at static type. Runtime, you have to somehow also look at dynamic type. Okay. And then just the other hierarchy, you can think about this as more like open-ended exam type of question. Given some hierarchy, you want to examine the different design method. Remember we talked about 3 designs in total. The first 2 without inheritance, and the last one with inheritance. Think about how you may actually implement this hierarchy over here using each of the methods. And think to yourself again, how each one of them is going to satisfy or violate the 2 design principles that we spoke about, cohesion and single choice principle. Right? So think about those issues there. That'll be a very good way to really also get prepared for the exam. All right, that's the running example we're going to do. Right? So we're going to take this example right away today and then build up some expectation exercise just to make sure we warm up for the rule of substitution today. Before I move on to the exercise today, guys, any questions from last time? Okay? Okay. So the plan will be today I want to talk about rule of substitution, polymorphism, dynamic binding, give you a little bit more formal definition. That'll be for today. And then on Thursday, I want to pick up from what we learned today and talk about typecasting thoroughly. Okay? That will be pretty heavy for this week. Okay? But you do let me know if you got any trouble. All right, let's now take a look at this exercise here. Okay? Let's say we want to figure out the range of expectation in certain location in the inheritance hierarchy. Okay? Let's pick 3 classes over here. iPhone 13 Pro, right here. Huawei P50 Pro, right here. Galaxy S21 Plus, right here. Right? Let's take these 3 classes and work out the range of expectation, meaning the methods you can call. There's no attributes in this hierarchy, just methods. Okay? So let's start with, let me just highlight about where they are. So for iPhone 13 Pro, it's here. And for Huawei model, it's here. And then for the final one, Galaxy S21 Plus, right here. Okay? So these are the 3 classes. You can see they somehow get located in different parts of the hierarchy. That will give you a very good idea about how to infer the complete set of expectation. One principle is expectation is not just about those methods you declare in that particular class only. You have to somehow trace all the way up to the top of the hierarchy. Somehow expectation got inherited or they got accumulated. So what do I mean? Let's take the first one, for example. So I'm here, iPhone 13 Pro. Oh, sorry. So we got iPhone 13 Pro over here. And each arrow over here represents extends keyword. So iPhone 13 Pro extends iOS. That means everything from iOS will be inherited to over here. Also, iOS extends smartphone. So everything from smartphone will also be accumulated or inherited to iOS. So the way we can accumulate the methods, you can either go maybe simply bottom up, or if you can see the path right away, you can also go top down. It's completely up to you. Let me go bottom up. Just follow the arrow. That might be the best way to do it as a beginner. So this will be the path I want to follow. Okay? I'll first of all go to iOS, and then I will go to the smartphone. Okay, that'll be the order. Okay, so now if I look at iPhone 13 Pro, first of all, I got a new method here, quick take. That one for sure is part of the expectation. So let's write it down quickly. So I would say QT, quick take. Okay, and then that's it. And now go up. So here you can see I got Surf Web and FaceTime. So I can put these 2. Right? However, notice that the Surf Web over here is not newly declared in iOS. It's already in the smartphone. It just got inherited. I can copy that down right away. That's okay. Okay, you'll be accumulated at some point anyway. So here we're gonna have FaceTime, and then we have Surf Web, and then we go again the arrow. We see dial, right? That's the complete set of expectation. You start from the class you're considering. Go all the way to the top, okay? Of course, if you want, you can also say equals method or toString is also part of the expectation. You can say that, but we normally don't include that unless we really have to. Question? One, yeah, huh? Sorry?
So everything in object you mean?
Yes, objects implicitly, yeah. So that's why we don't really do, unless it's really important for your tracing. Yeah, question?
Do you have to specify which class the function comes from? Because SurfWeb, we're inheriting it from iOS, not smartphone.
It's a very good question here. So here you can think about when we figure out expectation, it's really just about compilation. So when we talk about compilation, we don't really care which version of the method is being called. That's more like a dynamic binding at the runtime. So now just worry about if this method is part of the expectation. Right? Good. All right, let's do a second one, okay, all together. All right, this one here gonna follow similar logic. And then, let's see. So we start with zoomage, right? Zoomage, and then for here, so we're gonna go up. Let's see the path that we should go. We go up here to Huawei, and then go up here to Android, and go up here to smartphone. All right. So here, Huawei, no new attributes, no new methods. Go to Android, you got Surf Web, you got Skype. So you got Skype, and then you got Surf Web. And then go to the top, you got Dial as well. All right, so far so good. Let's now do the final one, and then we're gonna draw some conclusion from there so you can see some pattern. Okay, that's the most important thing I want to show to you. Okay, let's do one more. So this one here, again, Galaxy, go to Samsung. Samsung, go up to Android. And somehow you can see we're following kind of the same arrow here, which is okay. That makes sense. We call that this Android over here is a common ancestor for these two classes. Because when you go up from here, eventually you will meet in this class right here. Okay, that's just a term, right? The term about ancestor and descendant is something I'm going to define very soon. Okay. Just more like a general term about parents and child. All right, start from here. No new attributes, go up. And then we got side sync. So that one should be included. So we got side sync. And then we go up again, go to Android. We got Skype, Surf Web. We got Skype, and then we got Surf Web. And finally, go to the top, we got Dial. All right, you can feel free to try maybe other classes as well, but let me show you the pattern over here. That's the most important thing. Let's start with this. You can see we got Surf Web and also Dial right here. Okay, so all the three classes have certain overlap, like an intersection. Okay, so these are the common expectation that's inherited from the smartphone. Because somehow when you actually go all the way to the top, go all the way to the top, go all the way to the top, you always reach smartphone. So the expectation there will be accumulated to all these three classes eventually. Okay? So that one there is what we call the common expectation. Expectation inherited from, yeah, one moment, smart phone. Question?
What if there is a common expectation but doesn't actually have it? For example, if it wasn't Surf Web declaring the smartphone, but coincidentally iOS declares Surf Web and Android declares Surf Web, but smartphone itself doesn't declare Surf Web. So it's common between them, but it's not actually because of an ancestor. It's common between them due to coincidence.
You mean just the name happen to be the same, you're saying, right? Yeah, that one, yeah, I agree with you. That one could be, definitely can happen in practice. But when we kind of, whenever you mention the name, we kind of see we don't really have that kind of name confusion. But definitely they are different scope, for sure. Yeah, I wouldn't worry too much about it at this point. I wouldn't trick you on that. How about that? Okay. Yeah, go ahead, question.
So Surf Web is overridden in both iOS and Android.
Yeah.
But does that still make them a common expectation?
It does. So here, when we talk about expectation, is whether or not you can call that method. As long as you can call the method, the code is going to compile. That's all we are talking about. If you talk about which version of the Surf Web that's going to be called, either from the iOS version or from the Android version, that one is more about dynamic behavior. That's a different issue. Okay. Good. All right, good. Okay, let's make a little bit more pattern observation, and then we can move on. And then you can, okay, another one that's also kind of common. You can see right here. So all three classes have common expectation from smartphone. And then these two also have common expectation from Android, right? But not, iPhone 13 Pro has nothing to do with Android. Not really, because if you go all the way to the top, you never see Android. So the way to see that is right here. You can see here we got Skype, okay? Just a Skype. You can see for these two, right here, that is the common expectation from Android. Yes, that's the expectation from their common ancestor. For now, ancestor, you can think about parents, right? As many level as you like, okay? Ancestor, Android. All right, finally, you can see right here, for example, quick take and also zoom image, right? For example, these two, I can see these are the two that are specific to that particular child classes. So I'll put it here. So these are the child-specific methods or expectation. Okay. In this discussion here, I'm kind of using the term method and expectation interchangeably. Okay. So here, think about expectation is really about the method you can call. Expectation is really almost synonymous with callable methods. Methods you can call on that particular type without compilation error. Okay? Questions? All right. Let's now define terms quickly, and then we can talk about substitution. But before that, let's now talk about some definition. So the slides I'm actually going to go over is slide number 40, right? So that one there is pretty dense, lots of words over here, but don't worry, I'm actually going to talk about it and also visualize it one by one, okay? Let's first of all start with something very basic, just to clarify, okay? So to visualize a diagram like this, so let's start with 3 classes, for example. Let's make it a bit symbolic. Let's say we have 3 classes. We got Y, and also we got X, and also we got Z, right here. And then, so visually, whenever you draw any arrow, and the arrow has a direction, let's say Z points to X, that simply means we know that programmatically, say class Z extends X. You can think about the direction simply means extends in Java. And also X extends Y as well. So this correspondence is actually very crucial. So tomorrow or tonight, I'm actually going to give you the guide for written test number 2 for next Wednesday. And also I'm going to give you some practice questions as well. One of them is actually for you to somehow figure out or visualize the inheritance hierarchy given the Java class declarations using extends. So, but as soon as you see the question there and practice a little bit, it's not too bad. You just gotta be very fluent about doing it. Just whenever you got extends keyword from, let's say Z extends X, you simply draw an arrow between Z and X with the right direction. That's a critical principle. Okay. And it's also important to say the following. Z directly extends X. X directly extends Y. That would mean Z indirectly extends Y. Indirectly, okay? Let me write it down. It's a little bit like to say A larger than B, B larger than C. We know that A larger than C. Transitivity, okay? So that one there, let me put it. So we say that Z indirectly extends Y. Okay. Let's now define 2 terms, ancestor and descendants. Let's start with ancestor. Okay, so that's something we just spoke about, and then ancestor and descendants. And let's pick one class in the hierarchy. Whenever you talk about ancestor and descendants, it's kind of relative to one class you pick in the hierarchy, right? So we say the ancestor or descendants of a particular class. Let's say we pick this particular class right here, A, okay? Let's say we pick A here, somewhere in the middle. You can think about there are certain classes underneath it. There are some classes above it and some classes besides that, right? Just somewhere in the middle, arbitrary. Okay, let's pick A as a reference point. What's really ancestor? Okay, watch out for the definition. Okay, the ancestor classes of class A will be A itself plus all the classes that A either directly or indirectly extends. Okay, that's a precise definition. So what do I mean? Let's now highlight the ancestor for class A. Okay, I'm going to use green. It's going to be, first of all, A itself by definition. And the class that A directly extends. So far, 2 classes included. Also, all the classes that A indirectly extends. Because I know that A directly extends this directly extends this, so this one here should be indirectly extended by A. So that should be included as well, and so on. Right? We can go all the way to the top. Right here. You go all the way to the top. And just for your information, we said that this top class is called a root. Okay, just a special term. Okay, so when you guys actually get to 2101, the data structure course, maybe in the next term, so you will actually learn about something called a tree data structure, and you'll learn all sorts of different terminology about tree. But I'll just use some relevant ones in this course. So you only have to know what I mentioned in the lecture notes. That should be sufficient. You don't need to do anything extra. Okay, that's about ancestor. Okay, and what is so important about ancestor? What's so special about it? So the green one is something we call ancestor. Ancestors of A. Okay, it's now highlighted. Ancestor. Okay, number one. Let me write it down and then I'll visualize it. Basically, class A, right here, accumulates all the attributes and methods from its ancestor. Anything that's not private, of course. Okay. A accumulates or inherits. Accumulates all attributes and methods from its ancestor. For example, let's say if there's one method M declared over here, guarantee, it's going to be inherited all the way down to A, in guarantee, because everything will be inherited verbatim, right? Assuming that that one is not private. That's something assumption implicitly we are making. Okay? Consequently, since we kind of define attributes and methods as expectation, right? Remember the term expectation, right? So each class inherits all the expectation from its ancestor. So that would mean the expectation for that class is at least as many as the expectation for its ancestor. Okay, I'll write it down. So the expectation for A is at least as many. Usually it should be strictly larger than. You should always declare some new attributes or methods in that particular class. The expectation of any ancestor class. So number two comes from number one, really. But to really understand about all the rule of substitution or even the typecasting rule, we need number two. All right, so I would say after today, make sure you review this page and there's another page about rule of substitution before Thursday. Okay, question?
If A itself is an ancestor, then shouldn't it just be equal to? Like the expectation equal to?
Yeah, exactly. That's why I said larger than or equal to.
I mean, there's no way it's larger than than A itself because A is like the last.
So, okay, think about this operator here, right? There's a good question here. I like the precision you're thinking. Can I say 3 is larger than or equal to 3? Yeah, exactly. So A's expectation is larger than or equal to its own expectation. It just happen to be equal.
But it can be greater than. Like,
it cannot be greater. But in this, so here, when you say larger than or equal to, it's either larger than or equal to. Either way. If you get to either way, then you're okay. Right? So also, can you say 4 larger than or equal to 3? That's true, right? So now I'm giving you one example where it's exactly equal to that, or one example where it's larger than that. So both are true.
Yeah, I mean like if A itself is an ancestor, and then all the methods inside A are actually the expectation.
You can think about A itself is more like an edge case, right? So we're just comparing the expectation of A with itself. It should be just exactly equal to. But if you compare the expectation of A and its parents, usually should be strictly larger than because you got additional methods that's declared. Okay? All right, good. All right, let's now go the other direction about descendants. Okay, let's now look at definition first, and then we visualize. It's completely symmetric to descendants. All right, descendant classes of the same class A is going to be, again, A itself. Let's pause. What does that mean? A class A is both its ancestor and descendants, by definition. All right, just remember the definition is useful, actually. All right. So A itself and all the classes that either directly or indirectly extends A. So kind of symmetric. So let's now take a look on the diagram. So let me use pink for descendants. It's going to include A itself, first of all, descendants, right? All the classes directly that directly extend A. This level, right? You can see this class over here directly extends A. And this one here also directly extend A, right? Everything at the same level, basically. And also all the classes that indirectly extends A. So that means everything underneath it, okay? And we'll do a concrete example in just one moment. I think I'll just visualize the abstract rule first before we get to the example. All right, so the pink part over here is about descendants. And let's now do some remarks about descendants as well. All right. So we talk about descendants. Descendants of A. Okay. So descendants. Point number one, let's talk about what's being inherited. Anything you actually got as the expectation for A, which got inherited from all its ancestors, is going to be further inherited down to everything underneath A, basically. Right? Just the inheritance just always happen as soon as you have the arrow. So, first point. Expectation of A, we can think about attributes and methods. It is inherited to all of A's descendants. So now, how do you compare the expectation of A with any of the descendants of A's expectation? That's the thing, right? Go ahead.
Greater than or equal to A's expectation?
Yeah. Well, I think A itself should be less than or equal to its descendant. A descendant should be larger than or equal to, right? Yeah. Depending on which one you start with. Yeah. They're equally. Yeah. Good. All right. Okay. Number two. Let's write it down. You can think about the expectation of A should be less than or equal to the expectation of any descendant class. All right. This page here is straightforward. We're just talking about three things. Number one, we talk about how you can visualize about the extents and also understand what does it really mean to say one class indirectly extends another class. Okay, point number one. Point number two, we define ancestor. Given a particular class, ancestor will be itself all the way up to the root or the top of the hierarchy. And when you talk about descendants over here, you include the class itself and everything underneath it. And when you talk about expectation, all the ancestor is guaranteed to be less than or equal to for their expectation compared with A. Because A can declare some new attributes plus everything inherited. And if you compare the expectation for all the descendants versus A, it's going to be larger than or equal to. Because all of them are going to inherit whatever that's in A. Plus, they might declare some new attributes. For example, in this new child class over here, we might declare some method, maybe MA. So that's something new, right? Just to remember the principle we talk about what it can do in child classes. Just keep that in mind and review it. Okay. All right, let's do example right away. Okay, right here. Okay. And we choose three different classes to do exercise. And about expectation, that's really something we did earlier, right? Right in the beginning of the lecture. I'm going to leave that part for you exercise. You can definitely give it a try. Okay. So this part here is exercise. And let's now work out the ancestor and descendant. Let's just do a few so you get an idea. Let's say we get galaxy S21. First of all, how many ancestors? How many? Give me a number. 3? 3, 4? 4. Did you count the class itself? Aha, it's a common mistake, right? Okay, that's a very common mistake. Whenever you calculate the ancestor and descendants, make sure you count the class itself. So it's going to be Galaxy S21 itself, all the way top. Right? 1, 2, 3, 4. Okay, let's write it down just for this one here. So it's going to be Galaxy S21 and also Samsung. Also Android. Smartphone. Okay, 4 of them. How many descendants does this class have? 1, just itself, right? Good, very good. Okay, you get an idea. Galaxy S21, just itself. Okay. How about here, smartphone? How many ancestor? Just 1, because it's already up top, right? Itself plus anything it directly or indirectly inherits. You might be thinking, how about objects? Object is not inside this hierarchy, so we don't really consider object. You might be thinking 2, because object should be included. No. So this one here, ancestor, would just be smartphone itself. How about descendants? Yeah, just basically everything, right? So you can see the root of the hierarchy, its descendants will be just the entire tree, right? So I'm going to be lazy here. I'm going to say all classes. All right, and then for this one here, exercise for you, right? Very easy to figure out. Okay, question?
Can you explain why we count the actual class and ancestor and descendants, or is it just a convention that we...
It's more like a convention because somehow we're going to define the rule of substitution, and the substitution rule is going to be defined in terms of like an ancestor and descendants. And somehow you have to count the class itself in order to make the rule work consistently. Otherwise, you have to add always some side condition, which is not very convenient. Yeah. So it's also actually quite common. So later on, outside this course, once you get to 2101, you also have to somehow calculate descendants, ancestors, siblings, subtree, things like that. You also got some convention you have to follow. Yeah, just the way it is. Yeah. All right, good. All right. We got 2 minutes. Why don't we just do... Okay, how about this? I think we can do this. Let me spend about 2 or 3 minutes before I go on to generalize the substitution rule, which is another maybe 5 or 10 minute discussion. Before that, why don't I just summarize what you should know in general? You can think about this might be the last minute memorization you want to kind of remind yourself before writing the exam or the written test. But you don't really want to just memorize it. It's got to come with some understanding. But let's just give you the takeaway, take-home message first. Let's do this one here quickly, maybe 2 or 3 minutes, and then we'll take a short break. Okay. So we talk about variable assignments. You have, in the most general way, you got variable number 1 equals variable number 2. And the assumption is there is some inheritance hierarchy existing. And somehow the static type, declared type for variable 1, variable 2 are the 2 classes in the hierarchy. That's the assumption. Otherwise, you don't have to worry about this much. All right? So if you talk about students, or you talk about smartphone, right? Depending on which hierarchy you are involving in the discussion or consideration. So now the critical question goes like this. When we talk about substitution, you look at the equal sign, the variable assignments. You're basically asking, does this variable assignments compile? Does this variable assignments compile?
Assuming no manual testing?
Sorry, say it again.
Assuming no manual testing, right?
Yeah, of course. Let's assume there's no casting. We'll do lots of casting, don't worry, on Thursday. Yeah. Okay. Also, assignment here, there's also another more academic term people like to talk about when you talk about like an inheritance rule. People call variable assignment substitution. Okay? I'll talk about substitution as well after the break. Right? So it's called substitution. of course, just be aware, whenever we talk about variable assignments, people also might also say substitution. Okay? And how do we know? Since we talk about compilation, remember the principle? You only look at static type, right? That's the only thing you look at. Don't consider dynamic type. There's no tracing going on. So what you should do is you should really look up the declare or static type for variable 1. Let's say the static type happened to be, let's say T1, just some type. And look up the static type for variable number 2. Static type T2. T1 and T2 may be the same, may be different. Okay, so I'm talking about very general case. Okay, so here comes the so-called rule of substitution, meaning that judging to see whether a variable assignment should compile or not. So rule of substitution. And of course, that's in the context of inheritance. You somehow learn partially about what it should be, in the polymorphism intuition. We say the left-hand side must be the parents, the right-hand side must be the child. We just generalize it, okay? Left-hand side must be ancestor. Right-hand side must be descendants. That's it, all right? Now we're going to talk about why it should be the case after the break. So think about this. The rule goes like this. T2, the right-hand side, must be a descendants, which includes the possibility of being a child, right, of the left-hand side, T1. Okay? And the main justification, which we'll see after the break, when we visualize that tree over there, is because the expectation of T2 being the descendants guaranteed to be larger than or equal to, remember that ancestor-descendants definition there, descendants guaranteed to have their expectation larger than or equal to the expectation of T1. So this is the main justification that we have to visualize when we get to the generalization. Okay? Think about this one page is more like a summary. I'll just give it to you right away. Okay? Any questions? Okay, why don't we take a short break and then take attendance, and then we'll come back to define the rule. So let's now define the rule of substitution, and then after that we will be just able to do a series of examples just to emphasize, reinforce the understanding. Okay, so the slides I'm talking about right now will be, let me show to you. So before the break we spoke about actually accumulation, etc. Right? So these you can also go over when you study. Also expectation. All right, so I'm basically talking about slide number 43, okay? That one is about substitution. And also some visualization. I'll do that as well, when I talk about the rule. And then also the actual rule. So there are different scenarios you want to consider as well. So all these bullet points, you can go over them maybe after class. Let me just talk about them in a more intuitive way. So that will help you also read. So 43 and 44, all right? All right, let's now start with this. Whenever we talk about the rule of substitution, don't be too kind of distracted by the actual terms like a substitution. You're just talking about two things. Number one, variable assignments. Number two, compilation. These are the two things you're considering. All right, so first of all, let's start with the rule of substitution. It's basically just about, does a variable assignments compile? That's really what it is trying to define. Especially, you're looking at static type. Also, in the context of inheritance. That's really the keywords that we are trying to discuss right here. Okay? There's a compile, and also we got to consider the inheritance hierarchy we have, and also static type. So let's say we'll talk about it right here. All right. Let's now consider just 3 lines of code partially. Okay. I don't worry about what's on the right-hand side. Maybe some new keyword by calling some constructor, but that one's to do with runtime. I don't need to worry about it for substitution just yet. Okay. Let's say we got 2 variables. We got OA and OB. And then I want to assign OB to OA. That's my goal. All right? Let's now analyze these three lines to get a critical information. So let's start with number one for A. You can see here, A is a declared or static type for OA. So here, this is the static type of OA. And then we have right here the question mark, okay? I'm leaving that more like a placeholder, okay? So this thing here is going to be somehow placed by some of the classes right here in the hierarchy so that this variable assignment here is going to compile. We want to consider what will be the range of classes we can put in the question mark. Okay, that's something we're going to discuss. Okay, so this here is really denoting the static type of OB. Okay, and then we have actually this variable assignments right here. Right? Remember before the break we talked about the questions that we're asking. Right? Let's repeat the question just again. Right? The same question. Okay, we're basically asking. Right here. What can the question mark, which is the static type of OB, or the static type of the right-hand side, what can the static type of the right-hand side be such that the entire variable assignment is going to compile? All right. B, in order for this variable assignments. Or you can think about variable substitution to compile. Okay, that's really the critical question we're asking. What can this be? In order for the variable assignments or substitution to compile. Nothing about the runtime, just about compilation. All right. To answer this question here, let's understand roughly what substitution really is. And this, what I'm going to explain to you, somehow was already done once. Remember the proof by contradiction we spoke about in the intuitive idea about polymorphism? Something similar. Okay. Let's go from that route. Okay. So here, we are basically saying, right here, point number one. When we do this variable assignment, we are substituting OA by OB. Substitute OA by OB. But you know, it's just an English issue, right? You can either say we are substituting OA by OB. We can say we are substituting OB for OA. I think English-wise, they're all equal. But I'm just saying substitute OA by OB. That might be more intuitive for you. Okay. The way to understand this is after the substitution. Oh, what does it really mean for substitution? It simply means if the substitution compiles, assuming that it compiles, then you will be able to do things like this. Let's say before the substitution, OA points to some objects. OB also points to some objects right here. And then if the substitution compile. In that way, we're going to say OA, rather than pointing to here, is going to point to wherever OB is pointing to. So that's why we said, conceptually, OA has been substituted by OB's objects. All right? Just want to show to you what substitution can really be understood visually. So that means OA is not going to point to wherever OB is pointing to. Now let's think about the consequence of doing the substitution. So that's the key to understand the rule. After the substitution, if you look at OA, OA itself has the static type A. That means what we can expect to invoke on OA. is defined by right here. And what does the expectation come from? It's going to be from A itself, everything from the ancestor, as we said earlier. That's the expectation, right? So now, if we somehow want to really substitute OA by OB, we want to make sure that OB here should support at least as many expectations as OA. When I say should support at least as many, that means larger than or equal to. What does that mean? It's going to be a descendant class. Okay, I'm going to write it down. Okay. So after that, we expect to use. We expect to use the OA dot something, right? So here, let me just put just running out of space. OA dot. So it's got to be expectation. You can think about this part here is the expectation of A, which is the static type for OA, right? Let me say a little bit more about this one here. So let me put a star, okay? I put star here. OA's expectation must be fulfilled by the static type of OB. So that would mean the expectation, okay, so if you remember what we put there, the static type for OB is question mark. So that means the expectation of question mark should be larger than or equal to. Cannot be smaller than, because in that way, there will be some expectation for OA that cannot be fulfilled by OB. By the expectation of A. So this is really the critical conclusion we are getting. Okay, this one here. Okay, if you're okay with up to this point, so just one step further. When you say the static type for OB must be larger than or equal to for the expectation of A, that implies, yeah, that means the question mark should be a descending class, right? That's a one step. Yeah. Okay, so now let's go from there. So that tells us question mark here must be a descendants of A. And this is exactly the rule I spoke about before the break. But now I just give you a little bit more derivation. Okay? Let me recap, right? So when you revisit this page over here, you really want to somehow tell yourself some convincing story about what's going on. Let me recap it, and then I'll take a question. Okay, let me recap first. Whenever you have a variable assignment here, both sides have certain static type. For OA, the left-hand side has A, somewhere in the inheritance hierarchy. And OB, we're asking what can OB be for the static type, right? It turns out it can be any of the descendant classes, which will be A itself, and also everything underneath it. That'll be the descendants, okay? Everything here. So the green one is really what's acceptable when you put as a question mark. You can pick A itself and put it here. You can put this class over here and put it here, etc. Any of the descending classes. The reason is, whenever, assuming that this one will compile, you're basically substituting OA by OB. And OB itself must support all the expectation that's in OA. So the expectation for OB static type must be larger than or equal to. That means it must be a descending class. Okay, so that's the flow for logic. Question, sorry.
Actually check for descendants or expected methods. For example, if I implement another method which is
very good. Good question. Your fellow student asked a very insightful question here. How does compiler check for this? The compiler only check for descending class. It doesn't really figure out like what's the set of expectation and try to see if that one is larger than or equal to. That one I kind of introduced to give you more extra intuition to see why it should be like a descending class. So So actually, that's a very interesting project. Actually, for those of you who might be interested about beyond this course, don't bother right now. It's going to be too time consuming, which is to implement exactly type checking rule for programming language. Okay. Anyway. All right. So that's good. And then let me just write a little bit more notes. So this part here will be the descendants of A. Descendants of A. And we know that every descendant of A has its expectation larger than or equal to the expectation of A. Okay? So the green one here, it's a green light, so you will compile. That's about safe substitution. In the slides, it's also talk about unsafe substitution. Unsafe means it's not going to compile. So there are two scenarios. But of course, conceptually, you can think about anything that's not descendants, it's not going to compile. For example, if you put this class over here as the static type for here, it's not going to compile. If you put the parents of A into the question mark, it also is not going to compile, right? But let's now categorize them. So you can think about right here, the pink one. So this part here, starting from right here, okay? So for all these classes, starting from the parents of A, I cannot say these are the ancestors of A because that would have included A itself, right? So I should really say those are the ancestors of A's parents, okay? So think about here, that would be A's parents. If you put any of the pink classes here, it's not going to compile if you put it here. What about other classes right here? So we have here, here, and also here. Okay, let's do one example right away. Okay, otherwise you need some example. Let's say this is A. Let's say this is A. Ancestor will be so this is A. Descendants will be right here. These are the descendants, right? What about Huawei's parents' ancestor, which will be this part over here? But we're still missing other classes. Here, also here, 1 and 2. 1 and 2 here are something we call neither ancestor nor descendants. They also play some important role, especially when we talk about typecasting on Thursday. Let me say that again. If you pick this class right here, right, you can see descendants are right here. Huawei's parents is right here. So when you say Huawei's parents' ancestor are these classes. And also number 1 and number 2. So these are neither ancestor nor descendants. All right. Let's go back here. And the orange one over here will be neither, let me put it down. So the pink one here will be ancestor of A's parents. And B, the orange one will be neither ancestor nor descendants. So if you put any of the classes from A or B as a question mark, the static type of OB, it's not going to compile. All right, so that's a rule. All right, any questions? All right, let's now do lots of examples just to apply this rule. All right. Okay, let's start with this. This one here, you can see it's a variable assignment. And the left-hand side is all SP1, right? So let me just highlight them. SP1 over here, the static type is iOS. iOS. So this is the static type of SP1. As soon as we fix this class, which is A, what can be The static type on the right-hand side should be descendants of iOS, which will be iOS itself, iPhone SE, or iPhone 13 Pro. Only these three classes will be allowed. Anything outside this range, any of these, will not compile. As easy as that. Okay? So think about this one here is going to be descendants of SPs. Descendants of SP1's static type. So now if you look at that, let's say SP2, iPhone SE, right here, is a descendants, compile. SP3, static type, iPhone 13 Pro, is also a descendant of iOS, also compile. Okay? So in terms of the justification, let's say, I'll just give you one example, right? So either in the written test or maybe in the exam. For example, this one here should compile, right? Let's say this one here. Okay, I'll put it here. Compiles because there are two ways for you to write this. I will expect you to understand both, right? Number one, the static type of SP2, which is iPhone SE, is a descendants of the static type of SP1, which is iOS. Right, so that's one way to write it. Just say the right-hand side has a static type being the descendants of the static type on the left-hand side. The second one will be more about expectation. The second one there, you can say the static type of SP2 being a descendants can fulfill the expectation of SP1's static type. We're basically saying iPhone 13 Pro can fulfill the expectation of iOS.
Isn't 2 implied from 1? If it's descendant,
Oh yeah, I'm just saying you don't need to write both at the same time. You can write either.
okay.
Yeah, right. Pretty much like what you said earlier. One is more about how the compiler will check actually, but number two is a more intuitive thinking, right? So I would say both are acceptable. Yeah, unless I say explicitly which one you got to write. Right? Okay, so let's now do another one here. Guys, how about this one? Is it going to compile? So what you want to think in your mind is, what are the static type on the right-hand side? Is it a descendant class of the static type for the left-hand side? That's what you think, right? Let's now take a look. SP2, right-hand side, has the static type smartphone, right here. And SP1 has a static type iOS, right here. Yeah, so we are basically asking, is smartphone a descendant of iOS? No, just not. You don't necessarily have to say smartphone is an ancestor of iOS. It is, I agree. But I just gotta say it's not descendants. Yeah, that'll be more direct. Okay, so this one here is actually not gonna compile. Fail to compile. Because smartphone is not a descendants of iOS. All right. So not only that you have to justify why something will compile, you also need to know how to justify why something wouldn't compile. All right. All right, about 11 minutes. Let's do a little bit more example. I also want to define quickly polymorphism, dynamic binding as well, and then we're done. Okay. 11 minutes. All right, dynamic type very quickly. So this is also another small application for rule of substitution. So here we're saying, if you declare S to be of static type students, and we're doing a variable assignments, the only difference is now the right-hand side is not really like another variable. It's more like a constructor call you can think about. So this is not exactly runtime. We are trying to determine, can we actually assign S to the address of this particular new objects? we're asking the following. So the rule of substitution actually applies. We're asking, is resident student the right-hand side a descendant of students? Yes, compiles. Or another way, can resident students fulfill the expectation of students? Yes, it can.
So if you want to take it in the same way, then take it for an anonymous object if you want.
Oh yeah, of course, you can definitely replace this by object if you want to, but
You can take resident student as an anonymous object if you want to do the same thing as previous.
yeah,
Then
yeah.
do the descendants.
Yeah, anyway, yeah. So here, we're basically saying, let me write it down, this one here. So this one compiles because, again, you can write it in two different ways. I'll write it down just for the first time. Resident students on the right-hand side is a descendant of the static type of left-hand side, which is students. Or, I'm running out of space, I'll put 2 here. Or alternatively, you can say that the new, you can just say the resident students over here can fulfill the expectation of S static type, which is students. Okay, just a little bit application of object creation. You can think about the right-hand side, tells you the class directly. You don't have to look it up. It's right there. Okay. All right, let's now move on. Okay, let's see. Okay, that one's done. Okay, let's do a few more examples. And then I can assign some exercises for you to try, very straightforward. And then we'll talk about some terms quickly, and then we're done. Okay. Let's look at this example here. All right. So this one is something we did earlier, but just some quick check. Okay. You can see we got Jim and Jim. For these two variable assignments, should it compile?
Yes, because both are descendants.
Yeah, both are descendants, right? You can see resident students, non-resident students right here. They are both descendants of the left-hand side static type, which is students. All right? Okay, just in case I'm going too fast, no worries. You can always approach me after class, office hour. We can go over this again. But I'll write it down for you. Okay? Compile both of them. Because the resident students and non-resident students are descendants of Jim's static type, which is students. Okay? Or you can say alternatively, I'm just going to say that, you can say RS and RS can both fulfill the expectation of Jim's static type. You can also say that alternatively. Okay? How about this one? Is it going to compile? Yeah, wrong order, right? Exactly, right? You guys can hopefully get a little bit more better feel about what's going on here. It is important because things will get just a little bit deeper once we talk about typecast on Thursday, okay? Okay, so this one here, let me write down, not going to compile. Fail to compile. Let me write the intuitive way, because students cannot fulfill the expectation of Jeremy's static type, which is resident students. All right, just another way to write it. Okay. And then let's see. Okay. I think for the next two, you can definitely do exercises. You know, you can also find this answer on the slides. Okay, I'll leave the pages clean for you. Exercise number 1 and number 2. Okay. And then let's now do also this one here very quickly. So this one here is actually about tracing the dynamic type, right? Just to see how things can change. Let me just show to you. Okay, that's something we did kind of in the intuition example. Okay, this one quickly. So let's say we got 1, 2, and 3. Okay, let's say we are kind of tracing the dynamic type. Let's say after number 1, okay, we actually got Jim points to a student objects. So we know that at this point, students is the dynamic type for Jim. Okay? So rather than drawing a table, you can feel free to do that when you study, but let me just put it right here. Right after here, dynamic type of Jim will be students. Right here. So 1. Okay? And then we also got 2 other objects. We got RS, also we got NRS. Let me just visualize them quickly. So we got RS, which points to some resident students objects right here. And also NRS, which points to right here. NRS. All right, which is good. And then, okay, think about this is 2, this is 3. Let's now try to monitor how the dynamic type of Jim is going to change, especially whenever you got variable assignments, because you're changing where the reference is pointing to. You're definitely changing the objects being pointed to. So you might change the dynamic type. Let me call this number 4. And this one here, number 5. All right? You can double check yourself. Both of them should compile. Right? For example, quickly. RS, resident students. Jim, students. Resident student, descendants of that, compiles. Right? You can check the other one as well. So for number 4, we are basically doing Jim is assigned to RS. Rather than pointing to here, it's actually going to point to wherever RS is pointing to. At the same time, dynamic type for Jim is not going to be the same as the dynamic type for RS. Okay? Whenever you do reassignments, your ultimate object will have the static type, the dynamic type just the same as the object you're assigning to. So here, after this, dynamic type of Jim will be changed to dynamic type of RS variable, which is resident students. Okay, so that is number 4. Okay, for number 5, let me use a different color just to show to you. Okay, and of course, at this point, if you say Jim.getTuition, dynamic type is RS. So use the version from resident students, right? We said that many times. And then let's now do here. Let's say number 5. In which case, we're actually going to say Jim, rather than pointing to here, it is going to point to wherever NRS is pointing to. So this is number 5. And we know that Jim dynamic type has been changed to the same dynamic type as NRS. Right? Because they point to the same objects. Okay, let's write it down. Dynamic type of Jim has been changed to dynamic type of NRS, which is non-resident students. So when you actually call right now Jim.getTuition, because now dynamically, if you call Jim.getTuition here, dynamically it's now pointing to NRS. So you're going to call the version applying discount rate, right? Different version. Okay. Question? Okay. All right. Guys, question for you. How about here? Which version is it going to call? Okay, let me ask again. Okay. I'm asking, question is, which version of the getTuition is going to be called if we got executed at runtime? Okay, I heard you. And then? You will not compile. Now runtime exception. It does not even compile.
You said if it compiles, but I thought you meant if we did casting.
Oh, yeah. So, I think when we talk about if it didn't compile, it's more like about reasoning, right? So what happened is these two will not even compile. So you cannot even execute them, right? So these two will not compile, all right? So think about these two. Okay, guys, give me 1 minute. Let me write it down, and then we're just 1 page behind for section B. Don't worry, it's not your fault, it's my fault. I should have done more efficiently today. But we can do that 1 page on Thursday. Okay, so these two, not compile. Because if you look at Jim right here, has the student static type, right? Because students, yeah, exactly. Jim's static type is not descendants of the static type of the left-hand side. Okay, either RS and RS. You see my point? All right. So I think we just do this page maybe on Thursday. I'm running out of time. I don't want to take your time. So make sure you study the two rules and also ancestor descendants, and then I'm going to recap everything by using this page only, all right, on Thursday. All right, thank you. Again, if you got any question about lab number 4, you can go to WSC 105 tomorrow.